So when it rains on a soil surface or we irrigate, some of this water may infiltrate, meaning it will move and be absorbed into the soil profile. Some of the water may also be partitioned into runoff or evapotranspiration, but in this video I want to talk about infiltration. We may look at infiltration as a process in which the water content increases as a function of time as we look down in the soil profile. And what we may observe if we pond water on the soil surface or we are puddling water on the soil surface is that a sharp wetting front develops that will advance with time in the soil profile, and that this advancement starts to slow down. So you may summarize that a sharp wetting front develops under ponded conditions and that the rate of infiltration tends to slow down with time. So now let's look how the infiltration rate decreases with time. If we compare a dry soil and wet soil, we see that the initial infiltration rate into a dry soil is higher than that into a wet soil. And to explore why that is, we may consult Darcy-Buckingham's law. If you think about a ponded condition on the soil surface and a wetting front advancing into an initially dry soil, you would see that we have a relatively small hydraulic conductivity. The soil is dry, but we do have a very large driving gradient because the contrast between the saturated soil under the ponded condition and the dry soil that the wetting front is advancing into is very, very large. So we have faster infiltration into an initially dry soil than into a wet soil. And if we let the process go on, where now this saturated soil profile keeps advancing with depth, meaning that that wetting front keeps advancing with time, we would see that the hydraulic conductivity on average for the soil profile would increase with time, while at the same time the driving gradient would decrease because now more of the soil profile is saturated and the wetting front has advanced to greater values of L, which explains that the infiltration rate would have to decrease with time because the decrease in the driving gradient is no longer compensated by the hydraulic conductivity. And if we wait even longer, so now we're looking at really long times, we would see that the hydraulic conductivity eventually approaches values similar to the hydraulic conductivity because now the soil profile is completely saturated. While the driving gradient will approach unity, meaning that our infiltration rate, our volume per area per time, would approximate the saturated hydraulic conductivity of that soil. And we actually take advantage of that when we measure saturated hydraulic conductivity with a device called the infiltrometer. In the previous examples, ponding started right away on the soil surface. But normally that is not the case. Normally the rainfall or irrigation rates are lower than the maximum infiltration rates into soils, meaning that water will not start to pond until some later point in time. And up until this time of ponding, all the water that is applied to the soil surface, either as rain or irrigation, will infiltrate into the soil profile. And only after that will the infiltration rate start to decline in the fashion that we just explored. So what happens with the water that doesn't infiltrate? Well, that is the part that ends up being runoff and is really important for us to predict for things like erosion predictions. So lastly, what if the irrigation process isn't one-dimensional, but we have irrigation due to a point source, just as a drip emitter or like a line source, for example, an irrigation furrow? If we compare sand and a loam, you'll see that the wetting front in the sand would advance more in the vertical direction than in the loam case, where it'd be almost unidirectional. And it would of course be because in the sand condition, the gravity potential tends to dominate over the matrix potential in importance for that advance of the wetting front. So here we would say it's a gravity dominated process, and in the loam case, the matrix potential would be more important than the gravitational potential, and we get the more uniform distribution of water contents and more uniform advance of the wetting front with time.